Hello, everyone. Welcome back to the Preparing for the PAT course 2023. We will be getting started in just a second. We're letting our numbers settle down, which is always our first step, just to make sure that everybody has time to join us who would like to. But usually that only takes a minute or two. We're already up to almost 100 people joining us here on Zoom. So we'll get started lovely and quickly. Now, in front of you, you should be able to see a lovely picture of our physics department. Well, actually multiple pictures of our physics department, just giving you an idea of our buildings and some of the research that we do. I'm currently sat in the one with the trees outside with the weird square windows up on the top. Right, I am going to start our presentation for today. I think we are settled. So, hello everyone, welcome to the fourth webinar of the Preparing for the PAT course 2023. My name is Kat, my pronouns are she, her, and I am the Access Officer for the Department of Physics. And what that means is that I run most of our programs for secondary school students, including all of our stuff to support people like you who are interested in applying to study physics here in Oxford. This session is being recorded and will be made available to you tomorrow. In the meantime, a reminder of the housekeeping rules for those of you joining us on Zoom. You will be able to use our Q&A a bit later on for any of the questions that you would like to be addressed. I'll let you know once it's switched on and ready for you. You can also access the chat to share any of your thoughts or comments if you want to share your answers even. But we do ask that you keep it polite, keep it kind, and do not share any personal details or information, such as email addresses. Also, make sure you don't use it for any questions that you want us to answer. Keep those for the Q&A so that they don't get lost. If at any point you are feeling unsafe or concerned about anyone, you can contact me or our safeguarding lead, Sean Tadaldi. Let's get started now that we've got all of our admin notices. We've had lots of new joiners this week, as we do almost every week, which is amazing to see. And so I'm going to start with a really quick reminder of what the PAT is and what this course is. I won't take questions in this section. If I have time at the end, I'll hopefully take questions then. First things first, the PAT is the physics admissions test, and it is a required test that must be sat by all candidates for physics, physics and philosophy, engineering, and materials science. Your result on the PAT forms part of the information which admissions tutors use to decide who is shortlisted for interview. To sit the PAT, your school must register as a test centre and you must be registered as a candidate. In the vast majority of countries, PAT this year will be in a hybrid format with questions on a screen and a paper answer booklet that will be scanned and returned to us for marking by your teacher or whoever invigilates your test. The online test will also include a built-in calculator. This webinar is part of the PAT preparation course, which we run on behalf of all of the subjects who require the PAT, the ones we just spoke about, physics, physics and philosophy, engineering, and materials science. The Preparing for the PAT course is a set of 8 webinars, along with problem sets and summer assignments, that we hope will provide you with all of the information you need to take the PAT, to help you prepare for the PAT, and to be confident that you're going into interviews if you are shortlisted. The timetable on screen that I briefly accidentally brought up is at the bottom of every main PAT email, and it's always highlighted with where we are in it so that you can follow our progress over the next few months. In each session, I'll fill you in on any updates or news, just like I am now, particularly as we get closer to some of these key dates. Today, I've already said, is our 4th webinar. You can see us highlighted in the yellow colour on this slide. In the first week, we had a session led by Rachel, who is a teacher who works really closely with us. She gave us a really whistle-stop general problem-solving session, which was great. She included things like dimensional analysis and lots of hints and tips about using diagrams and notation. Following that webinar, we shared a set of problems which two of our undergraduates then took through the solutions to in the second webinar. Last week, we built on our general problem-solving strategies, and we looked at problems which benefit from a slightly different approach and a second glance. Problems that maybe if you take the traditional method, turn out to be a lot harder than they need to be. Today, two of our undergraduates will take you through the solutions to problem set number 2, which was shared at the end of that session. If you haven't had a chance to watch any of those sessions or to try the problems that we're going to be looking at today, they're all available on our online PAT course materials page, which looks like the slide you can see. The introduction to physics problem solving, right at the top, is a more detailed look at some of the concepts that Rachel discussed in the first webinar. Then underneath, all the links are clearly related to the webinar. Sorry, all the links related to the webinars are clearly labeled and set out in order. Now, the link to this course materials page is sent out in all of the emails that come around. So you don't need to go hunting for it now, don't panic. And the page is updated after every session, really clearly labeled so that you can find everything that you need. Finally, just a quick reminder that all of the other information that both you and your school need can be found at this page. Again, this is shared in the email that will come around tomorrow morning. This is the most up-to-date page, and it's the one to check for any information that you need, and it's got a really useful FAQ page. The most recent update is that school registrations to become a test centre are now open, and there's a link on that website for this. It might sound like a really big deal and like a huge thing that you need to organise, but trust us, your teachers are used to this behind the scenes. They do it for all of your other admissions tests, external exams. They will be ready for this. Your school will get all the details for this. You don't need to worry about it, but do feel free to mention to your teachers that your registration is ready, particularly if your school are new to the PAT, and then they've got time to contact us if they've got any questions as well, just like you were able to. A quick note here, if you are applying and you do not attend a school, so say you've taken a year out or something like that, you can apply to sit the test at a school that is a registered test centre, but you'll not be able to do that until candidate registrations open on the 1st of September. The test format, which I mentioned earlier, the hybrid where we've got questions on screen and then a written answer booklet, is a new one. It's not a big change though. The questions will be really similar. The syllabus is unchanged from last year. Even though I can tell you it's not a big change, we don't want anyone to be feeling anxious about it. So you will be able to access a trial version of the test screen so you can see what it looks like in advance. It's not quite ready yet, but I'll update you and show you the new format as soon as it's ready. That is my quick PAT introduction and update. I hope it was helpful. The only other thing I always like to remind people is that if you have any accessibility arrangements in place for normal exams, they also hold for the PAT. Just need to apply for those as you go through the process of registration. Hopefully we'll have time for questions at the end, but for now, I'm going to stop sharing my screen. I'm going to hand you over to our two lovely undergraduates, Adam and Helena, who are going to take you through the solutions to today's problem. So stop screen sharing, come on back, and I will introduce you to Helena and Adam, who will take you through the problems that you were set last week. I'll share the link in a chat as soon as they both switch on their cameras and are ready to start presenting. And once they are ready to go, I'll switch on the Q&A so that if you have any questions about what they're presenting, you can pop them over there. Please, for now, keep the Q&A specifically for questions for Helena and Adam. If you've got any general PAT questions, we'll deal with those at the end. It just helps us keep everything in the right place. Helena and Adam, welcome. Lovely to see you both. Thank you for joining us. Feel free to give us a wave.
Oh, thank
you. Amazing. And who is starting us off? Who's doing the first question tonight?
I think, yeah. So I will just share my screen.
Lovely. In that case, I'm going to turn my camera and microphone off. I will move over to moderating the
Okay, so hi everyone. So I'll be starting off with the first problem today, which is a quite a long mechanics problem called marble in a fishbowl. So basically, it says this fishbowl has some height 4r/3, such that the top of the sphere is removed. So it has. Get my pen out. Yeah, yeah. It has radius r. So this is the center. And height 4r/3. Now, a ball is launched from the bottom of the bowl, and the rim is parallel with the ground. So so this is the ground. Um, and a ball is launched at some speed from the base of this bowl. And the question is, assuming all this is frictionless, and of course ignoring air resistance because we're doing physics here, find the maximum initial velocity that could be given to the marble for it to land back in the fishbowl. So we want to know what the maximum value of this, I've called it V naught, is. So I think the first thing we notice here with this problem is what we really care about is the velocity of the ball when it's here, when it's exiting the ball. So let's call that V1. And I'll just draw a line across here. And we're also, let's call this distance from this edge to this edge of the bowl X. Right. So by conservation of energy, we can say that the sum of the kinetic and potential energy of the ball here and sum of the kinetic and potential energy of the ball here has to be equal. So here it has zero potential energy. So the total energy is just, so by conservation of energy, is equal to half, and the ball has some mass m. So half m v naught squared, and that's got to be equal to half m v1 squared plus mgh, which is mg times 4/3r. So just equating these two, we can see it's independent of the mass. So therefore we know that v1 squared, just multiplying through by 2, is v naught squared minus 8/3 gr. Yes. So let's just put this equation to one side for now. And I don't have enough space for this, but I will sort of move along. And so we have this expression for the initial velocity in terms of the velocity at the top. So now what we want to find is V1, the maximum value of V1 for which we can launch this. So this is some angle theta, and this is just a projectile motion problem now at the top. And we can find theta from the geometry of this problem. So we know this has radius r, and this is therefore r, and this bit is x/2. So what we want to find is, first of all, what this value of x is, which we can do. Give me a second here. We can do this by Pythagoras essentially. Because this is theta, and therefore this is theta. And sorry, give me a second here. Um, right. So, right. Okay. So this bit, because this is the center, that means this height has to be r, and therefore this bit is r/3, right? Because we know the total height is 4r/3. So we know this side is r, this is r/3. So by Pythagoras, we know that x/2 the whole squared has to be equal to r squared minus r/3 the whole squared. And from this, if you work through it, you get that x is equal to 4√2/3r. So that's this length across. And then we can also use this r and r over 3 to get the angle theta, which is adjacent over the hypotenuse. So that is cos theta is equal to r over 3 over r. So 1 over 3. So that makes theta yeah. So oh yeah, that's cos theta. And also we can get a relation for sine theta from the relation we have for x. Because that'll be useful later when you get these projectile motion things in terms of sine and cos. So that is so sine theta, the opposite, which is x over 2. So that is 2 root 2 over 3 over r. So r times that. So it's just 2 root 2 over 3. So those are expressions for sine and cos. So now what we want is the value of V1 that will give us a part that just has a range of x over 2. So this is now just a straightforward projectile motion problem, where um where the where we want to find the range. So the range formula for projectile motion we get first by finding in the y direction the amount of time it'll take for the thing to happen, for the fall to happen. So we divide this v1. Let me just redraw it further up here. This bit of the problem. So when it's launching at v1 at some theta, it has a y component, call that vy, and an x component, call that vx. And clearly vy is equal to v1 sine theta, that's the vertical component, and vx is equal to v1 cos theta. Now the time it takes for the part to intersect back with the ground, we can use the Suvat equation, s is equal to ut plus half at squared to find the time taken. So what we want is where s is the height along the y-axis, where this becomes 0. And we know u here is vy, sorry. So that's v1 sine theta t minus, because g is acting in the negative direction, minus 1/2 g t squared. So here we can see that one solution will be 0, right? And one solution, so we can ignore that. That's essentially the launch point. That's when time is 0. We can ignore that and say that t is equal to 2v1 sine theta over g, and we know the value of sine theta, right? That's 2 root 2 over 3. So 4 root 2 over 3 v1 over g. Now the range in that time, because we know that in the x direction gravity has no effect, that's you can just use speed as distance by time. So therefore distance is equal to speed, so the speed in the x direction into time. And the limiting value we want is when the distance is equal to x, where x is this distance across the fishbowl. And we know the value of x. We know that is 4 root 2 over 3 r. So we want 4 root 2 over 3 r to be equal to vx, which is v1 cos theta. So let me just substitute that in directly as well. So v1 times 1/3 times time, which is 4 root 2 over 3 v1 over g. So a lot of things here cancel. So this, and this. So we have that yeah, so we have that V1 squared is equal to 3GR. So this is another expression that's useful. Right, so let's call this expression 2. So we have an expression for V1, and then we have a relation between V1 and V0, and we want to find V0. So plugging this 2 into equation 1 and just rearranging a bit, we get V0 squared is equal to V1 squared plus 8 over 3 GR, right? Because V0 is the speed at the bottom. And therefore V0 is the root of 3 plus 8 over 3 GR, which is 9 plus 8, that is 17 over 3 GR. So that's the answer. It's not a very nice looking solution, but it's you get a neat round number from it. And that is the maximum speed at which you can launch the marble for it to circle back around into the fishbowl. Because if you had it any higher, it would just escape beyond the edge of the bowl, and if you had it any smaller, it would fall back in. And again, so it can be up to that. So it must be less than or equal to 17 over 3 GR, the whole square root. Right. So should I just have a look through the questions? Okay, that is so there's a question, what length is x over 2? That is half the length of the gap between the 2 points of opening on the fishbowl. So that is the gap between this point and this point. And then there's a question from Sean, which is asking, could you not just launch the marble directly upwards with any velocity? Well, any velocity below the escape velocity of the Earth, yes, you could. But I think the way the question is phrased, oh yeah, the way the question is phrased, you could argue that. That's fair, but I think the way they wanted you to interpret it is you're launching it sideways. But yeah, that's a very fair answer. I'm not sure what the reaction of a PAT examiner would be to saying that. But yeah, if you said it could be anything less than escape velocity and it'll land back in the fishbowl, that is
I'm
technically
just going to come in there, Adam. I think one of the most interesting things about the PAT problems is that quite often it is what assumptions you make that determine
correct.
how you solve the problem. And all of them are individually marked. All the answers are considered on their own merits. So if you make a weird assumption, you're good to go. I'm totally with you.
Right. Yeah. Yeah. That is a very funny way of looking at it, and I mean that certainly simplifies your problem. So I mean, if that works, go for it. So there was another question asking why I added 3 plus 8 over 3. Sorry, that's slightly me writing slightly confusing notation. We're trying to solve for V0 here. So I brought this over to this side, and so I added it.
Awesome. Adam,
And
I'm going
yep,
to make a suggestion. If
yep.
we switch over, if Helena presents question 2, could you respond to some of the questions in the Q&A by text?
Cool. Yeah, we'll do that. Yeah.
Amazing. Thanks so much. That way, we'll get the best of both worlds. Thanks so
Right.
much,
Yeah.
Adam. That was a great answer to question 1. Helena, over to you.
All right. Hi everyone. I'm just going to share my screen and then we'll get going. Okay, that should share in a second. Okay. So this problem is about 2 trusses that are attached like that with a ball in between. So the ball's weight 500 newtons and is suspended at the apex of the structure. Each truss is length 3 meters and the mass of the ball and mass 40 kilograms. And we have a 3-meter rope connecting the 2 trusses that's tied a 1/6 of the way up. and the structure is on an ice rink, which means we can assume no friction between the base of the trusses and the ground, and we're calculating the resultant tension in this rope. So I think for questions where you're given a lot of numerical information like this, the clearest way to interpret it all and to show the examiner what you think, how you're interpreting the question, is to draw a diagram. So I've drawn a diagram below, and as you can see, you've got these two tension forces acting on the rope, and that's essentially what we're trying to solve for. I've drawn the weight of the two trusses and the distances that, so obviously the weight of the truss acts from the midpoint, and because the rope is connected a sixth of the way up, you can, and the truss is 3 meters long, you've got this bottom section here that's 0.5, and this upper section here is 2.5. Now, first of all, I'm going to balance the vertical forces. So just because of the weight's 500 newtons. The ball is weight 500 newtons, and the weight of, and so we've got 500 plus 2W of the forces acting downwards, and this is equal to 2R, which are our two reaction forces acting at the points of contact with the ground for the trusses. And we can just simplify that to write R equals 250 plus W. Okay, so that equation, let's call that equation 1 for the moment. And so now looking at the question, we want to pick a sensible point to calculate the forces. We want to pick a sensible point to take moments about. And the obvious point here to use is the apex. So the very top is the point we're going to take moments about, because then we only need to consider 3 forces. So because we need perpendicular directions, we're going to decompose the forces in this diagram. So just adding a few more arrows, we've got the weight, the perpendicular component of weight is W cos theta, because this angle here, yeah, so that's W cos theta there. And then for this tension force, the perpendicular component here is going to be T sine theta. And then for the reaction force acting here, the perpendicular component in this direction is R cos theta. And hopefully we're not given the angle theta, but we should be able to calculate it later from using trigonometry. And obviously this, because of the symmetry of the problem, these forces are the same on this side. So now we're going to take moments because we've worked out the perpendicular components. So we can say that W cos theta times 1.5, which is the distance of this force here from this point. So that's our first force. And then we're going to add, that's a moment acting, that moment's acting in this direction. So we've also got the tension force acting in the same direction. So we've got T sine theta times, and that is 2.5 meters from our apex. And then that's equal to the clockwise moments. And so that is equal to R cos theta times 3, because that's our distance of this force from our point that we're taking the moments about. So this equation doesn't look very nice right now, but I'm just going to call it equation 2. So this equation we can manipulate quite a lot. So if we multiply the equation, so by manipulating this equation, if we multiply it by 2, then we're going to get 3W cos theta plus 5t sine theta equals 6r cos theta. Then we can rearrange so we have t sine theta equals 6r cos theta minus 3w cos theta over 5. And then we're going to use this fact up here that we worked out earlier to sub in for r, so that we get everything just in terms of, so we get an expression for t just in terms of w. So we're going to r equals 250 plus w. Subbing that in, we get t equals 6 250 plus w cos theta minus 3w cos theta over 5 sine theta, because we've just to isolate t, we've divided by sine theta. Okay, and we can write this as t equals 1500 plus 3w over 5. This is just expanding the brackets and simplifying, times cos theta over sine theta. Okay, now we need to get rid of the thetas, essentially. So we're going to use a bit of trigonometry. So if we look at this diagram up here, we've got a triangle formed by the central rope, one of the trusses, and if that goes all the way down, this triangle here that I've just highlighted, I'm going to redraw down here with the correct lengths, and we should hopefully be able to use this to solve for theta. So this triangle, we've got 2.5 here, which is the length of the truss until the rope. The rope length, we've got angle theta, and then we've got 1.5 and 2. So this is the triangle we form based on the information given in the question, and which is shown on the diagram. So using this triangle, we can clearly see that tan theta, which is equal to sine theta over cos theta, that's equal to 2 over 1.5. And we're also given in the question that the weight of the mass, which is the mass of each of our trusses is 40 kilograms. And so if the mass is 40 kilograms, we can assume the weight is roughly 40 G, which is 400 newtons approximately. So subbing in all that into equation 3 up here, we can say that we've got T equals 1500 plus 3 times 400, which is our weight, over 5 times, we need 1 over tan theta, which is 1.5 over 2. And simplifying this expression and expanding, we get T equals 405 newtons, which is the correct answer for the tension in this rope here. I'm going to hand back over to Adam to do the next question, and I'll answer any questions about this solution in the Q&A.
Thank you so much, Helena. That was great. I think you've only got a couple, so it shouldn't take you too long to type those out. Adam, welcome back. You all set and ready for question 3?
Yes.
Awesome. Yeah, I can see your diagram now. Time for me to switch off.
Okay, so this is another projectile motion problem. This is a bit more broken up into 3 components. So that there were a couple of questions about the last one about how much work went into one question, but this is fairly typical of a PAT question. You have it broken up into several subsections or slightly smaller, more manageable chunks. So the first bit is quite simple, pretty much standard A-level problem, I'd imagine, which is show the maximum range of a cannon on flat ground is achieved when the angle is 45 degrees. So yeah, let's call it oh no color. Let's call this V naught. Oh, there we go. V naught. So I could go through all this again, but we've done this in the last problem, which is we found the time taken for it to intersect the ground in a straight line is this. So 2v1 sine theta over g. Oh, here v naught sine theta over g. And the distance r here is equal to the horizontal component v x, so that's this. This is Vy. Vx, G downwards. Vx times time, where Vx is V cos theta, V naught cos theta. So V naught cos theta times 2V naught over G sine theta. Which becomes V naught squared over G 2 sine theta cos theta. Now there is a trigonometric identity which simplifies this, which will give you V naught squared over G is sine of 2 theta. Now this again, I think is a fairly standard trig identity, but they will normally tell you the trig identity you need to use. Like they put it again as a hint on the question. So sorry, let me just right. Yeah. So this is the range. Now what we want to do is max. So you don't actually have to use this. You could just use the chain, not the chain rule, the product rule to do this derivative and maximize it. But this just makes things a bit neater. So we have r as a function of theta here, and equal to that. So now we're trying to maximize this. I mean, yeah, maximize that. So therefore, dr over d theta is v naught squared over g dot 2 cos 2 theta. This is just using the chain rule, and that has to equal 0. So for this to equal 0, clearly cos 2 theta has to equal 0, which means 2 theta has to be equal to 2 theta has to be equal to pi over 2, right? Because cos of 90 degrees. We're doing this in, did they say, do they want the answer in degrees or radians? Oh, they wanted the answer in degrees. So it's 90 degrees. And therefore, the launch angle has to be 45 degrees. So yeah, you do it. Knowing this trig identity makes it a lot easier, but you could also work this out through sort of trial and error by substituting it into this first expression, this 2 sine theta cos theta, and you would still get the right answer, especially since it's given, right? You could just substitute that in and get 0, and then you know you've got the right answer. Right. So that is part A. Now moving on to part B, where they've complicated things. So they say the can's at the top of a hill with an incline of phi, then rewrite the equation as that. So again, we know what we're working towards, and that does make life a little bit easier. But they have seriously complicated the question. So this is the hill, it's got angle phi, then our cannon's still here, launching at angle to the horizontal theta. So the complication here is that our range calculation initially was based on the fact that the projectile returns to the height at which it started. Whereas here, essentially, the ground is moving downwards the further along the thing travels. So it's going to be dependent on the slope of this. Sorry, this should be a straight line, but yeah. So this is some angle phi, and it says it has got So yeah, let's say this is the range of the cannon. Let's call this R. And therefore this is also phi. So the distance it falls is R tan phi, because opposite over adjacent. So R tan phi, or rather negative R tan phi, is the final Y value. So the Y at the intersection point is minus R tan phi. So we just go back to the beginning and use that Suvat equation, S equals UT minus half GT squared. And here S is the Y, which is minus R tan phi. U is our Vy, which is V naught sine theta t minus 1/2 g t squared. Again, the negative sign here is because g is acting downwards. Now solving for t, it's just a quadratic, and what you get is time is equal to, and I'll spare you the algebra, but this is just a quadratic equation. It gives you v naught sine theta plus or minus root of v naught squared sine squared theta plus 2gr tan phi, the whole thing over g. Now that gives us the range, which is the range is equal to the time times v of x, because v of x doesn't change because it's perpendicular to the direction of the gravity, the acceleration. So you can just use uniform velocity. And vx is v naught cos theta. So that means so v naught cos theta times t. So now this is quite a nasty expression. And what we're trying to find is that the range is this very neat thing. So v naught, so just multiplying each component, we get v naught squared sine theta cos theta over g. Plus right. Oh yeah, and here the time is got to be positive, because assuming all these values are positive, if you take negative solution, that's negative time. So it'll give you essentially solution is for if you backtrack. So if you go back and find whatever intersects with this point, that's what the negative time value would give you. So you have to take the positive root of this. And we right. So this so now we've got an expression for R, but it is a bit of a mess at the moment. So you get v naught squared over v naught cos theta over g times root of v naught squared sine squared theta plus 2gr tan theta. And what you do, the whole thing's under the square root. And what you do is now move all these terms to this side. So r minus v naught squared over g sine theta cos theta is equal to v naught cos theta over g square root of v naught squared sine squared theta plus 2gr tan theta. And what you do now is you square both sides. And again, this is slightly painful algebra. You square both sides to remove the square root sign, and then you solve a quadratic for r, which gives you And if anyone wants me to go through the algebra, I can, but in the interest of time right now, just write out what you get for R initially, which is U squared G tan phi. And you also use these relations to simplify sine theta cos theta, so you get half sine 2 theta. And so from that, you get U squared G tan phi cos 2 theta plus 1 plus U squared G R tan phi. Oh, sorry, U squared G sine 2 theta over G squared, which is equal to U squared over G. Wait, sorry, U is equivalent to V naught here. I changed my notation midway through. I apologize. Sine 2 theta plus tan phi times 1 plus cos 2 theta, which is the answer we were asked for in the question. So here you are very much looking for a solution, and you do need to use some trig identities to solve it. But once you've got the setup, it's just algebra, and it's fairly straightforward. It's just a lot of lines of calculation, and some trigonometric identities. But again, identities you wouldn't be expected to know, except what's listed in the syllabus. So just check that. So now we want to maximize the range. So we have R. So again, we've got to take our dr over d theta. That's the final part of the question. They want us to find what the maximum range of this incline is. Or the relation between the angles to get the maximum range on our incline. So that it would just be u squared over g times 2 cos 2 theta plus minus 2 tan phi sine 2 theta. I think that's right. And then that at a maximum value is 0. So we just care about this expression in the brackets, really. So dividing through, you get cos 2 theta sine 2 theta over cos. The cos 2 theta is equal to tan phi sine 2 theta. Therefore, tan of 2 theta, just taking this over to this side and that over to the other side, is equal to cot phi. Cot phi. And this is the relation they want. So if it's maximum when the launch angle is, the tan of the launch angle is twice the cotangent of the incline of the slope. And what we can do then is actually simplify this further using the property that cot phi, I keep writing cos, cot phi is equal to tan of pi over 2 minus phi. And therefore you can just take, because it's tan on both sides, we can say 2 theta is equal to pi over 2 minus phi, which means 2 theta plus phi must equal 90 degrees. So what we can do is a sanity check on this answer, which is if there's no hill, if it's on flat ground, we should land up with the same answer as earlier, which is that if we set phi to 0, so flat land, then our theta, 2 theta is pi over 2, therefore theta is pi over 4, which is 45 degrees, which is the same answer as before. So it kind of makes sense if we just check it with our first answer. Which is again a useful method of checking your solution. Just plug it back into the original, plug it into a simpler case, so an edge case of, let's say we launch this horizontally, or let's say we just launch this vertically, and see what happens. And if it intuitively makes sense, you're probably on the right track in terms of a solution. But yeah, I will hand this over again, and I will answer your questions in the chat.
Awesome, thank you, Adam. I like the little problem-solving tip there at the end about sense checking your solutions. I think you've got 6 or 7 questions about the algebra. I think people agreed that the algebra was a little bit tricky on that one. So I think we are ready to hand over to Helena, question 4. Helena, I might need you to stop sharing your screen though, just to warn you. There we are, awesome. Hi Helena, welcome back.
Hi, thanks, Adam. Right, let me just share my screen again. Okay, hopefully this next question should be slightly less directly intense. Right, this question is called Monkey Shoot. A zookeeper's trying to tranquilize a monkey, and so there are two different situations, and the first part of this question is literally just an explanation of what you think will happen in each of these cases. So question A here. So if the monkey doesn't move, how should the zookeeper aim? Well, if the dart's going to accelerate downwards, then due to gravity, the zookeeper should try and aim above the monkey so that it ends up hitting the monkey. And so that's quite straightforward and intuitive. And similarly for part B, if the monkey were to let go of the branch, if you imagine the typical experiment with the feather and the rock on the moon, if you assume no air resistance, then you'd assume they would fall at the same rate because acceleration is the same. So they both have acceleration G acting on them. And so the zookeeper in this case should just aim at the monkey because both the dart and the monkey will fall at the same rate. So that's the simple explanation part to this question. The slightly more complicated bit is confirming this. And the most straightforward way to confirm this is by having the arc, by looking at the path of the arrow and the path of the monkey and finding out where they meet to confirm that this is correct. So as usual, it's helpful to draw a diagram. So this bit over here is the dart and this here is the monkey. So the dart has an initial velocity and is horizontal distance sx away from the dart. And if we assume y equals 0, where the dart is launched, the monkey is at height h. So looking at this triangle, we can find it quite a useful expression, which I've just set out over here, for the angle theta, which is the launch angle of the arrow, so that it hits the monkey. So firstly, let's consider the x direction. Essentially, what we're trying to find out is we want to work out an expression. The thing that will be the same is the time in both the horizontal and vertical directions. So we're going to we're going to try and find an expression for the time. So looking in the x direction, sx equals uxt plus half axt squared. But if we're assuming no air resistance, ax equals 0. So we're going to lose the second term. So we're just going to get sx equals uxt. And so t equals sx over ux. And ux we know from because we've called the launch angle theta. So we have sx over u cos theta. And so this is an expression, I'm just going to write it, t equals sx over u cos theta. This is equation 1. This is our expression for the time it takes the dart to reach the same horizontal displacement as the monkey. Now this time is the same. This time should be the same as the time it takes the dart to reach the same vertical height as the monkey. So we're going to use this fact for the next part of the problem. So sy equals uyt plus half ayt squared plus h. So that's the vertical height moved by the arrow in this time. Is here we have, you look at this problem, uy equals and because h is our initial height here, and the monkey, if we're looking at our monkey, the monkey starts from rest. So we have uy equals 0, and sy is our time it takes the monkey to fall, and that is half. Sorry, the distance the monkey falls in this time t, which the expression for which we have up here. So sy is half ay t squared plus h. And so ay, we know because it's in the vertical direction, is just minus g. I've just chosen the convention for acceleration as upwards, so gravity is acting downwards. So and so using the expression for time we found earlier, we can find sy equals h minus g sx squared over 2u squared cos squared theta. So this is monkey. Now we're going to consider the dart. So for the dart, sy equals uyt plus half ayt squared. Now uy here, because we're looking at the dart, is just u sine theta. And we know that for the dart and the monkey to be at the same place at the same time, the time t is the same as our expression we found up here. So subbing that all in, we're going to get sy equals u sine theta sx over u cos theta. And acceleration is also the same. Minus g over 2 sx squared over u squared cos squared theta. And rearranging and cancelling, we're going to get that equals tan theta, or sx tan theta, minus g sx squared over 2u squared cos squared theta. So finally, substituting in the fact that this geometry of the problem that we worked out up here. So we have, just writing that down here to help us. So tan theta is h over sx. Substituting that into the problem. So this is sy. We can finally see that sy equals h minus g sx squared over 2u squared cos squared theta, because tan theta, the sx cancels, so you just get h. And so we can see that since this is our vertical displacement of the monkey, and where's the expression? And this is excuse me, this is our vertical displacement for the dart, and this is equal to the vertical displacement we calculated here for the monkey. And since they're the same, the zookeeper needs to aim directly at the monkey, so that if the monkey is falling at the same rate as the dart, so that they will hit in midair. So not a particularly challenging problem. It just requires you to draw a diagram and think about it clearly and use the information given it through the job. Label the quantities you're using carefully, and then use them throughout the question, and the algebra works quite nicely. But I'm going to look at answer any questions left for me and hand over to Adam for the next problem.
Thank you.
Thank you, Hannah.
So I will share screen again, and it is a bit of a mess from the last one, but this is mercifully a slightly simpler question. And this is motion time graphs. So there are 3 different cases you're asked to look at and sketch. So if I'm being honest, this is, in my opinion, more of an interview question, actually. This is sort of a classic interview type question where you'd be asked to see how you sketch out these different kind of very wordy scenarios, but there are not that many numbers involved. So this is, first one is a ball is thrown up in the air and caught at the same height. So basically someone's throwing a ball up and then catches it. So here, so they want 3 motion time graphs. They want the acceleration versus time, velocity versus time, and displacement versus time. So the first of all, the acceleration time for this, it is just a free fall case. So time, acceleration, let's call this A, B, and C cases. So the acceleration versus time for this one, it's just, or rather, actually, just redraw this. Rather, it's a constant negative acceleration. So with time, there's constant negative acceleration of g. Right, because the ball is always having something acting on it. And the velocity time, therefore, because acceleration is velocity is just derivative of acceleration, so it's going to be a uniform negative slope. So it's going to start at some positive velocity, right? Because it's thrown up with some initial velocity. Let's call that v0, and it's going to just fall down. And then when you catch it at the same height, that means that just by the symmetry of it, it's going to have a final velocity that's the negative of that. So negative v0 will be falling down as fast as you threw it up. And then the displacement time graph. So y against time is it's again the derivative of this. So you're going to end up with, if it's a straight line, then the derivative will be a parabola, and it'll just do something like this, as you would expect. It goes up and then slowly reaches its peak and then starts free falling again. And it reached some maximum height, maximum height h, let's call it, which I again, they haven't given you any numbers here, so that we don't have a way of calculating that, but that's roughly what you get. Right. And the second case, what they ask for is a train travels. So this is a very simple initial start to this problem. The second case is a train travels from Birmingham to Oxford, stopping at Banbury only on the route. You may assume the journey is in a straight line, and it only takes a few minutes of constant acceleration or deceleration to get to its top speed or come to a stop. So basically, most of the time it's traveling at a constant speed, and after each stop, so coming into a station, it'll decelerate for a bit, and then it'll accelerate, and then the acceleration stops. So that means that the acceleration, essentially, we're looking at a square graph. So this train is going from, let's say, with time, it starts at, saying it's going from Birmingham to Oxford, but yeah. So goes Birmingham, then it gets to Banbury, then it gets to Oxford. And this is just with time roughly in the middle. So now our acceleration versus time. So it pulls out, this is a 0 point, it pulls out of Birmingham, and it'll have some positive acceleration. Let's just assume that's uniform for the sake of the argument. So it's some uniform positive acceleration, and then that drops to 0 once it reaches its maximum speed. And then it has that constant speed until it's pulling into Banbury, at which point it decelerates. And then it stops at Banbury for a while, so there's no acceleration. And then when it leaves Banbury, it accelerates again. And then reaches a constant speed. And then when it reaches Oxford, it decelerates again. And then comes to a halt. So yeah, sorry, it's connecting lines across here. So that's our acceleration against time. Again, a little bit more complicated, but essentially it's what you'd intuitively expect. Train accelerates out of a station and then stays at the same speed all the way through. then stops right before it comes into a station, speeds up again, and then leaves it. So now from this acceleration graph, we can get our zoom out a little bit so you can still see this one. We can get our velocity. So we know the train starts from a stationary point. I mean, it starts when it's at rest. And at this uniform acceleration, it'll go up to a constant speed. And then let me just draw lines down here. Yeah. So this is just intervals in time so we can see what happens when. So then across all this bit when it's cruising, it just has a constant speed. Then it decelerates. So it'll go down on a straight line to 0. Then it's at the stop. So it's at station. And then it goes back up again to its line speed. At its line speed for a while. Then it decelerates again. And it stops at Oxford. So that's its velocity as a function of time. And therefore, its displacement as a function of time, which we know is going to be, as it's accelerating, it's going to be parabolic. So it's going to be something like, let me again just draw these lines down to keep things easier. So as it's accelerating out of Birmingham, it's going to be like a upward parabola, like x squared or something. So it's going to be going up. I should probably just, because we need to, yeah, just do it at the bottom because we need a bit of space for this one. Because, because intuitively with the train, you know, the displacement is always going to be increasing, right? It's always heading in the right direction, either increasing or staying the same. So it's initially going to increase like that, right, when it's accelerating. Then at this constant speed, it will be increasing linearly. Then it decelerates, which means it starts slowing down. Then it stays, when it's at the station, it just stays at the same place. Then it curves up again, leaving the station. Then it increases linearly along the line. And then it slows down and comes to a stop. And this is the distance between Birmingham and Oxford. So this is the total distance the train traveled. Sorry, it's kind of exceeded my graph. But that is the thing of the train. So again, not much math. You just kind of have to think your way through it. And if you work step by step and break it down into little bits, so leaving Birmingham, entering the intermediate Banbury station, leaving the intermediate station, coming into the final station. If you just think that through what's happening, it's a pretty easy problem to work through. Then the final one is a football is dropped from a great height. So it's reached its terminal velocity here, we're including air resistance. So it's reached some high final speed. It bounces inelastically, so it loses some energy. But air resistance can be ignored. So it just bounces, and then when it hits the ground, just the friction with the ground and the sound it generates and all that make it lose some energy. And then it bounces up again, and then it hits the ground a second time, and they want us to sketch it until it hits the ground a second time. What we want now is the acceleration. So it's reached terminal velocity. So what that means is the effective acceleration, because you have the gravitational pull, obviously, and then you have the air resistance pushing it up. So at a certain point, those forces cancel each other out. So the net force, therefore the net acceleration on the ball becomes 0. So when it starts out from the great height it's being dropped from, it's got an acceleration of negative g, right? It's in free fall. And then over time, that tends towards 0, and then it effectively becomes 0. So it's terminal velocity at this point. And then it hits the ground. So when it hits the ground, it's being bounced up, but very quickly. It's going to be a very sharp acceleration. So it reaches terminal velocity, it's falling for a bit, then it hits the ground. So it's literally just going to be a spike. And because as you think about it, the velocity just changes, it just flips. And then at that point, it says air resistance can be ignored. So that means it's slowed down so much, it's being affected by gravity again. So it's at this negative G. So it's in free fall again, and it has this velocity, this acceleration. So this is our acceleration graph. And this is slightly trickier, and you may not get this completely intuitively. It might make sense to sketch the velocity first and then come back to this. So then our velocity, yeah, it's free falling. So first it starts from rest, right? And then it's when it reaches this free fall point, again, let me just mark that. So it kind of, this is the terminal velocity, and it kind of falls until that, because the acceleration is slowing. So it slowly approaches this terminal speed. And then it maintains this speed, and then it hits the ground. This is where it hits the ground. And then at this point, again, the velocity sort of flips. So it comes back in the other direction, but it's inelastic. So it comes to some v, let's call this v2, and this v2 must be less than the terminal velocity in terms of magnitude. So this negative vt. And now we're just under free fall, and we know what happens under free fall. It is just a uniform linear slowing in the velocity. So it'll go up for a bit, and then it'll start falling again. And then it reaches a second bounce, which will spike back up again. And the same here, you suddenly have a spike back up, but it's a smaller one, second bounce. Right. So that's the velocity. Now the displacement from this now is fairly self-explanatory. Now this shouldn't be too tricky, because we know it's starting from a great height, and then it falls. Sorry. And it falls. So it starts here, and you have this inverse parabolic thing, and then as it reaches the terminal, sorry, let's redraw that. So you have this inverse parabolic thing, which is slowly, as it reaches terminal velocity, that becomes linear. So it just reaches this linear thing, and it then hits the ground. Sorry, this is a straight line. Then it hits the ground, and then it bounces. So again, this is just a sharp point, and it bounces, and that is just, typical. I mean, the same as part one, right? You just end up with this sort of shape, inverse parabolic thing, and then you have your second bounce, and yeah, and it just goes on from there. And it would, I mean, they only sketch the second one, but basically what would happen is it would just keep getting smaller and smaller and smaller, and then peter out. So yeah, those are your three sketches. So yeah, a nice simple question there, relatively, and no numbers. You have to think it through and create some sketches. Hopefully you can create nicer looking drawings than I can. But yeah, I will hand back over to Helena now and answer any questions you may have.
Awesome. Thank you so much, Adam. And you're drawing on a screen. You're doing absolutely fine. So we have two more questions to come through today. Helena's going to take question 6. Then Adam's going to take our final question 7. Helena, over to you.
Thank you. Okay, so this question is an electronics one, so a bit of a change from the mechanics. This question, although the diagram looks quite tricky, it's not too bad. You just have to break it down and redraw the circuit step by step. I think the trick is trying not to skip too many steps at once, because otherwise you can end up miscalculating and missing things out. So I think just a quick reminder, I'm sure you all know, but I just thought to jot it down here. The two things we use when we're redrawing circuits is addition of resistors in series and parallel. So this top one here, series in a series connection of resistors, you just add them. And in parallel, this is the expression, which I'm sure you've all covered in school. But we will use these two expressions for the resistance of any of different series and parallel networks in this question. Now, when I initially solved this question, I subdivided each part into a different area and just calculated these different A, B, C, D in turn, and then put those back in, because each of these parts doesn't really change the structure of the circuit. So if you do this, you get these values, and you can then just get a circuit if you sub these values in that looks like this one down here. But I'm just going to go through it a little bit more slowly, just so that it's clear to everyone. So if we look at this section A first, we can add these two 10 ohm resistors to get a 20 ohm resistor, which you can see here replaces this section. And then we can also add, if you look at part B, we can add all of these three resistors here together to get 100 ohms. So if we do that, we arrive with the circuit that looks like this first one here. Now, if we keep adding, now we can do some adding in parallel, because those were all the series additions. So if we add the two 20 ohm resistors in parallel, and then we're going to add these two resistors in parallel, and then we're going to add these two resistors in parallel. So doing that, we're going to get 10 ohms up here, because 20 and 20, when you add them using that parallel formula, you just get 10. And then the 10 and the 40, when you add, you get 8. And the 24 and the 24, you get 12. So we now end up with this circuit arrangement here. So essentially, it's then just a case of rearranging your circuit into a simple formula and continuing to combine your resistors until you get to something that looks like this bit up here, which is just the battery with one resistor representative of this rather nasty looking network on the left. So if it can be quite hard to see, but essentially you need to keep the points in this, you need to make sure all the same wires go into the same point. So this wire here, you can sort of turn around here, and you'd have your 100 ohm resistor, and you can see that instead of this bit here, if you took this bit out, you can write it like this, which is what this diagram down here does, just to make it easier to simplify. You can then see that between this terminal and this terminal, the 25 ohm and the 100 ohm resistor are connected in parallel. So we can add those two together, and then you can see that you've then got, so we're going to have 1 over, so when you add those two together, you've then got a resistor here in series with the 8 ohm. So you've got a 20 ohm resistor here in series with the 8 ohm resistor, which you can then add to give you this setup, which I've drawn down here, where you've got 28 ohms, then 4 ohms, then 28 ohms again. And adding these to the 28 and the 4 in parallel, you then get this circuit here. And so that we get the arrangement where you've got a cell and then essentially RT here, we can then say that RT equals 31.5 ohms. And that's, I think, all this question was asking. Yeah, that's all the question asks you to do, just to find RT. So it's not a particularly difficult question if you just tackle it step by step and are really systematic with your addition in series and parallel. So I'm now going to hand back over to Adam just to tackle the final circuits question.
Thank you so much, Helena. That one felt significantly quicker than a few of the others, didn't it?
Yeah, it's strange. Some of the questions are much easier than others, so it's about picking off the easier ones, I
That's
think.
nice though. It gives us an idea of the kind of variety that we're up against for the pet. Adam, it's over to you for question 7. Thank you so much.
Okay, so let me just share screen for the final time. Oh, I can't share when you're sharing, Helena. Sorry.
Sorry. We'll just stop.
That's okay. Thanks.
Yeah.
Yeah, got that. Right. So this final question, which I've got here, let me just move that down. Um, just move that out here. And I will, so with this question, basically you have this cube of resistors, and we're trying to do what we did in the previous question, which is work out the overall resistance of this setup. So there's current flowing into A, and we want to find out what the resistance would be at each of these points. So there are, well, I forget how many vertices there are on a square, but yeah, so at each of these vertices. So your initial first thought is just flatten this out and then solve it the resistor network. Problem with that is you end up getting these overlapping wires. So whichever way you try to crush a cube, because it's 3-dimensional, you're going to end up with 2 layers overlapping, right? And so your sort of naive way of solving it wouldn't work, which is somewhat frustrating. But luckily there is, because this is a cube and it's a very symmetric setup, there's a nice sort of neat argument to simplify the problem, which is so from node A, current has to flow evenly because of Kirchhoff's current rule, right? Which is the current must part so that the current leaving must be equal to the current coming in, and because it's all symmetric again, it just has to be split evenly. So each of these is getting 1/3 of the current, which means that when it reaches this, essentially these 3 points, B, H, and F, are all equivalent. They'll all be an equivalent there'd be an equivalent resistance drop, there'd be an equivalent voltage drop across all of them. So what we can do is, because they're all equivalent, we can pin them together. So in effect, what that looks like is if we try to flatten this out, you end up with A, and then you have your 3 resistors in parallel, and then they all link up again. And this point is B, H, and F. Now, the second bit gets more tricky. So each of these nodes, because the current has come in from this side, it has to leave through these 2. So each of these, again, by symmetry, is taking I/6. So B goes to E and C, A goes to H goes to C and G, and F goes to G and E. So there are basically 6 resistors in parallel here, because you could pin them all together again and you have 2, 2, 2 going into each one. So you have your 6 resistors in parallel. That is 6, yeah. And then this is points C, E, sorry, this actually is point, is that? This is point C, E, and G, I think. Wait, B is going there. Yeah, C, E, and G. And then finally, so points C, E, and G are all fed from this side. Right. So they all must go into D, and this is your output. So they all go into D. C, E, and G go into D. So essentially the same. If you look at how at the symmetry of it, it's essentially the same setup as this A going to B, H, and F. So it's 3 resistors coming in parallel, and you can join them up. So for D, it is again just 3 resistors in parallel, going from that node from these 3 nodes out to D. So this is basically the problem solved at this point, because assuming they're all 12 identical resistors of resistance R, and therefore this parallel arrangement would just have resistance R over 3, right? Because 1 over R plus 1 over R plus 1 over R is equal to 1 over the net. And then this network has R over 6. This network has R over 3 again. So at B, H, and F, the resistance, what does it ask for? Yeah, the resistance reading in each position. So B, H, and F, the resistance reading would be R over 3. So this is equal to RB, H, and F. And then at C, E, and G, because it's in series, it'll be the sum of these two. So that'll be R over 2. So R over 3 plus R over 6, which is R over 2. And then the resistance of D, which is the other end of the cube, is you just add another R over 3 to that. That'll be 5R over 6. So just this plus that plus that. So the resistance increases as you go further along the cube, as you'd expect, but you end up with an answer that's a lot lower than you probably thought it would be initially. And this can only be solved by exploiting the symmetry of it to simplify it. And there are multiple ways of approaching this. This is one way. You can also get some other networks. You can solve it as a parallel system as well. So there are many, many ways of approaching this, and it all ends up with the same answer. This is the sort of easiest way to get the answer for all the nodes. So that's about it from me. I will just answer the questions in the chat, I guess.
Amazing, Adam. What impeccable timing. 7:58, no less. And actually, and in your final comment, where you were talking about different solutions, I think you've even answered one of your own Q&A set questions in advance, where somebody was asking about alternative methods. So thank you very much. Helena and Adam, it's been amazing. Thank you so much. You guys are both more than welcome to turn off your cameras now. I know, Adam, you're going to answer a couple of questions, but once you are done, you are free to go. Thank you so much for joining us. I think we'll see you both later in October. All of our lovely potential students. Oh, sorry, Helena.
No, I just to say thank you.
No, I shouldn't have spoken over you. You're very welcome. It's been lovely to see you. If there are any quick questions on the PAT in general, I have 2 minutes. So if you pop them into the Q&A, I will be able to do a quick fire answer. Adam, would you be able to stop screen sharing for me as well, please? That'd be great. Thank you so much. Let's see what lands in the Q&A. Usually this lands us with a lot of quick questions. Oh, so far though, they are all for Adam rather than for me. If you don't have any questions, please feel free to go away and enjoy your evening. We will see you again for a webinar in September, but there are going to be some summer assignments coming through and all sorts of things over the summer. So keep an eye on your emails. Oh, and I've just got one question, which will take us to 8 o'clock perfectly, where I was asked, which buildings do the physics undergraduates use? So our physics campus is split into 2 main sections. In one section, we have the undergraduate teaching laboratories and then a load of research facilities that you will probably not see while you're an undergraduate. And then lectures are over on our other building in Clarendon. Okay, so huge range of buildings. Have a look on our website. Oh, and I've got a PAT question, which I'm not entirely sure about the answer to. So I will check about the dictionary. So, I've had a question, sorry, asking me, can you bring a dictionary to the PAT if English is not your first language? I'm not 100% sure. I would check the PAT exam page. And if you can't get an answer, send me an email and I'll look into it in more detail for you. The pet mentoring program that has closed for applications. We're not taking any more questions for that, I'm afraid. And if you do not qualify as an international student, you have to take an English exam. If you're a UK student with other qualifications that demonstrate your English ability, I wouldn't think so. Again, have a look on the PAT page. If you can't find an answer on the FAQs, send me a specific email. You'll have all got my email because you all got the link to today, and I will help you out with that. One more question. General question, are the questions on the practice workbook similar in difficulty compared with the PAT? We think they're really good preparation, but your best bet would be to have a look at the past papers and find out for yourself. And no, there is not an unofficial formula sheet, I am afraid, that we know of. There might be one kicking around. Thank you so much, everyone. As ever, you are welcome to drop me any emails, and I do reply to every question that I get sent through. So don't feel that we're abandoning you just because we didn't get to your questions today. I am going to call an end to today's webinar. Look out for your emails tomorrow morning, where you'll have the recording and lots of other information to see you through the summer. Thank you so much, everyone. Bye.